So we're going to go through it very, very quickly. So primarily the questions come from the final versions where students are not able to incorporate all the previous versions into one final version. So the idea is very, very simple. So we're going to steal some of the code here. Okay. So just a bit request, a recap. You're asked to write a program, ask user for a new password. A new password is valid if it satisfies the following conditions here. And I extract each of these conditions here as one version in the previous questions. Okay, so if you are able to solve each of these versions here, you should be able to solve the final version but incorporate all of them together. And if the new password is valid, then you do the following, which is if the value of current password is an empty string, you store the new password as current password. If it's not an empty string, you append the current password to the list of previous passwords. That means you move the current password to the previous password to store as a history, and then update the value of current password to the new password that is valid. Okay. And of course, if the password is not valid, you display to user the new password is invalid. So this part here, update user password, is almost the same. Okay. So here, except this part here. All right. If it is valid. Okay, update new password if it is valid. If it's valid, the new password. So if it's not valid, then you display that the new password is invalid. Okay, so we're gonna modify here and there to satisfy our conditions here. Okay, if it's not valid. Okay, if it's valid, so this will be false. Then you check these conditions here, which we have done in many previous versions. If it's empty string, then you just assign new password to current password. Otherwise, you move or append the current password to the previous password. This is a list, all right? And then only you update the value of current password with new password. All right, so now what is valid? Okay, so validity comes from here. So valid is a variable, okay, that we need to define. Okay, so it has many conditions. It's not equals to current password. Okay, so new password not equals to current password. If it's valid, it must not equals to the current password. And it's not equals to any of the strings stored in the previous password. Okay, so and new password is not actually not in the previous passwords. Okay, so again, you just have to reformat it in a way the Python can understand. You know that to translate this code here, it just means that new password is not in previous password. And we know that new password in previous password will return true if it's in, otherwise it will return false. So we need a negation here. So, and not this, okay? So we have first condition, and then we have a second condition, all right? And what is the third condition? It does not contain username in any letter case, okay? And username is not in new password dot lower, okay? Because the username is lower cases, and I don't care which case it is. So what I'm going to do is that I'm going to make new password dot lower. This will create a copy. It doesn't change new password. It just create a copy where every characters in new password now is in lowercase. So I only concentrate whether the username, which is already in a lowercase, is in new password dot lower. Okay, and what else? What is the third condition? What is the fourth condition? And it contains at least one digit. Okay, so we have has digit here. Check if it has digit. So we're gonna add it has digit. And the last one, it contains at least one small case alphabet. So we're gonna have one more here. This is part of one of the version that you have. It has one small case alphabet. Okay, so we have as alphabet. So the idea checking whether it has certain property that we want is always the same. We always have a variable that initialized to false. And once we found it, we're gonna make it into true. Okay, so for I in range what? So of course, if you for this particular lab, I wanted you to learn how to use the character encoding. Okay, so for small case alphabet, we're gonna check, for example, you want to use ORD, okay, which is return the integer representation of a character string. Okay, so it will be ORD of A, small case alphabet, all the way to ORD of Z plus 1, because we want to include order of Z or integer representation of Z. Remember, this represent the end value, and when we do range, this is the start, we include the start, does not include the end, but we want to include ORDZ, so we need to add plus 1 here, okay, so that it include ORDZ itself. Okay, now X equals to CHRI, that means X now is the character represented by the integer, and if X is a new password, has alphabet equals to true, and then you break. Okay, so now we will have our has alphabet here. Okay, so now you basically create a new variable that contains all the conditions for which the new password is going to be valid. Okay, so this is everything that you need to do by combining all the conditions, and then that's it. All right, so the idea is pretty simple. You use the previous versions, all right, and if it's not valid, you say that it's invalid. Otherwise, the previous version, you already done this part, okay? And what is valid? Then you start defining what is valid by combining all these conditions together, okay? And here, for example, not int is created in this form so that it understands that we wanted to check that its new password is not in the previous password. And then we have something like has digit and has alphabet. Now, these are done previously before we start creating this variable, okay? Now, that's the end for this code here. It looks complicated, but if you look at this, these are all part of the versions that you have done in the previous exercise that you have done here, okay? Now, one thing I want to mention here is this part here. So we have started about finding whether it has a digit. We're also finding to try to find whether it has alphabet. So the idea we do is always the same. We look for what value that you want to look for. Okay, in this case, I'm looking for a digit. Okay, so I look at all the possible digits, and then I check whether it is in the list or the string that I'm looking for. And if I'm looking for alphabet, the idea is that I look through all the alphabets and check whether each of these alphabet is in the string that I'm looking for. If it's in the string that I'm looking for, good, I found it, I stop. Otherwise, I will continue to look for the second alphabet to check whether it is in the string, okay? So this kind of idea of checking whether an element is in the string and where the space is checked, in this case, the space is checked, first cases is all the digits, second case is all the alphabet. These are called brute force search, which is the topic for today, okay? Where we enumerate or we write down all the possibilities that we want to search for. When we want to search for something, not a particular value, but search for something, we look at all the possibility that we want to search for. When we want to look for a digit, we search for all the digits. When we want to look for alphabets, we search for all the alphabets. And this is called exhaustive enumerations. We write down all the possibilities, okay? So we enumerate or we list down all the possibilities until we get to the right answer, or we exhaust the space of possibilities. That means these are all the possibilities. 0 to 9 are all the integer or all the digits, okay, that could exist in a text, okay? If we check each one of them and none of them exists in the string, then we are certain that it does not have digits, okay? And this is called we exhaust the space of possibilities. All right, let's start with, let's formalize the idea of exhaustive search. And then we see there are examples for which we want to implement our own search and for which we want to change our search space and so on. And we will come up with different versions of searching based on different scenarios. And we're going to analyze which one is more efficient in particular. Okay, so the very simple idea, we start off with a very simple example, is that we want to search for a particular element in the list. Okay, suppose you're given a value, an element X, which is initialized to some value, and you have a list, and you want to check whether X is in the list. And of course, okay, so say here, before you do search, okay, so you have a list of some values, and then you want to find whether 12 is in X, 12 is in L, okay? And of course, this is a small list, so you obviously see that it is in L. But if you have a large list, okay, you don't want, it becomes difficult for human to check each one element whether it's equal to L. And luckily for us, we have a built-in method, a built-in operator, int. Okay, so you're going to check X in L by just running this code, X in L itself, literally. Okay, it will give you either true or false by executing this operator. It say that X is in L, 12 is in L. Okay, but if you weren't given this operator here, or you are curious of how it executes this, okay, so let's give it a try. If you were to do it by yourself without using the built-in operator, how would you do it? What kind of algorithms, what kind of instruction you want to give to the computer to discover whether X is in L, okay? So X in L, it runs some certain operations behind the scene. What are these operations? How did they do it? How did they find whether X is in L? So the idea is very, very simple, okay? Which is you go through every element in the search space. In our case here, we have a particular value X. We want to search for 12 in L, okay? So our search space can be the list itself, okay? And then at each iteration, you check if the element in the space that you search is equals to X. If yes, you just output true and break, and then you stop, okay? So you output true, and then you exit or break. All right, at the end of the iteration, you have exhaust all the possibility. Okay, so the idea is if X exists in L, then one of the element in L must be equal to X. Okay, so you know that if it exists, it must belong to one of these elements in L. So the idea is this is my search space L now, which is my list. I'm going to go through every element in L, check whether it's equals to X. Okay, so it's very easy. So I'm going to go to, for every element in L, I'm going to check if element is equals to X. If element is equals to X, means I found it. Found is equals to true, and then you break, you exit. You don't look for further. You already found it, and that's the end. All right. So what is found? When you create a variable, okay, you make sure that, if you remember when we talk about creating a variable inside if statement, will give you trouble if this if statement is never equals to true. Okay, so before that, when you create a variable inside the if statement, you should initialize it before the if statement. In this case, we initialize even before the for loop. So found is equals to false at the beginning. It is initialized to false. All right, and it will change to true if you have found it. Okay, at the end of the iterations, you have exhaust all possibilities. All the element in L has been checked. None of them is equals to X. So you know that found is stay as false. Okay, so now you can say if found. So if it's found, you can print that X is in L. Else you can print, for example, X is not in. Print true or false, up to you. Okay, or alternatively, you can just print found itself. Right. So whether it's true or false. So this is consistent with the built-in operator X in L here. So this is true and this is true. So let's look at another element, say 1, 2, 3 here. If I use the built-in operator, it say that it's false. Okay, let's try this. It also said it's false. So our own version of checking whether X is in the list is consistent with the result of the built-in version. Okay, Now, again, the whole idea is to let you get used to this algorithm of exhaustive search. You want to search a particular element in the list. So you look through every element in the list, check whether it's equals to X. Okay. Now, another version or another formulation of enumeration, exhaustive enumeration, is not just about searching. Okay. We can, for example, generalize this idea to count. Okay, count for an element X. Well, the idea is to, when you want to count something, you basically also implement some kind of search. When you want to count an element in list, you basically also need to search for this element. And when you search for it, you also want to count at the same time. So the idea is, okay, so let's give, for example, L equals to this and X equals to 1, and we want to count. You can use the built-in method. Count to search for it. So for example, L.count X will return the number of times X occur in L, which is the number of times 1 occur in L. So apparently L occurs 7 times here. Okay, now this is using built-in methods, and as always, we wanted to know how can we do it ourselves by implement this .count ourselves. Okay, so let's implement it ourselves. The idea is very much the same as before. Okay, so we're gonna build on top of this one. All right, the idea is the same. So to count X in L, okay, so we're gonna go through or iterate the search space, which is L itself. Okay, and in each iteration, we check if the element is equals to X. If yes, I don't output true and exit, because I want to keep on finding it, because I want to count the total number of times X is in L. Okay, so if yes, well, I'm gonna make a change here. Okay, I'm gonna count, so I'm gonna add 1 to sum, where sum, so create a variable for sum, which initialize to 0. Okay, we have seen this idea before, we just formalize it. Okay, so if you found when you go through iteration, you examine each value. If the element is equal to X, which is the value that you are looking for, yet you want to count, you add 1 to this variable sum here. Okay, and then continue with the next iteration. You don't stop because you want to keep counting. Maybe there are more X occur in the subsequent elements in L. Okay, and at the end of the iteration, you don't output force, rather you output the sum itself. Okay, now before that, I want to mention something. So sum, okay, is actually a function. It's a functioning. If you create a variable called sum, then you lose this value. You lose the functioning sum itself in this collab here. Okay, so sum is a function name, so I might want to change it to, say, total. Okay, because sum is already a function name, I don't want to have a conflict, because once you define sum is equal to 0, you can't use the sum function anymore. It becomes a value rather than a function itself. So I'm going to change it to the name variable called total, for example. Okay, so the idea will be the same as what we have earlier on. Okay, just a simple modification. All right, but you use the same idea of searching. Again, whether it's we iterate through the element in L. Okay, instead of found equals to false, I'm going to have total now equals to 0. Okay, and if element is equals to X, I'm not just flipping found from false to true. I'm going to add 1 to count. And I don't break it. I'm going to continue it. Okay, and the end, I'm going to print total. So the blueprint is still the same. We go through every element. We check this element satisfies certain property. If it is, what do we do? If it's not, what do we do? And at the end, what do we print? Okay, so for example here total 1, which is 7. So again, you can use you can check this is what you implement, and this is what the built-in method. They both give the same values. So it indicates that for this particular value of L and particular value of X, your implementation is correct. Okay, so the idea is always has been the same. You first identify the search space, identify the property of the element you want to search for. Okay, in the first case, we look for whether the element is equal to a particular value. In the second example, we do counting. Again, we are searching for that particular element. Okay, and identify the output once the element is found. In the first case, once it's found, we stop. In the second case, once we found it, we continue. And before we continue, we add 1 to the variable called total. Okay, and what would be the output if the element doesn't exist in the search space? Okay? In the first case, it will remain as false. In the second case, where we do counting, then we just end it. Then the value of total will be the final number of times X occur in the list L. Okay, now there are other sort of flavor that you do the same thing. It's not just searching, it's not just counting. Say you want to, for example, identify the index or indices for all occurrence of the element X. Okay, again, it looks like it's not searching, but it is. In the essence, it's a searching. You basically do the same blueprint of searching as before, but you just make a very little modification. So again, you are searching. So we essentially we are searching for X. Okay, so we basically use the same blueprint as before, but make modifications. Okay, so certain modifications. So we're gonna go through every element in the list at each iteration. If the element is equals to X, so it's yes. We don't add 1 to count or anything. Okay, we just print the indices, index of X. Okay, and then we continue with the next element. And at the end of the iterations, that's the end, do nothing. Because we just want to identify all the indices for all occurrence of element of X. Now this time, because we are concerning about the index, okay, instead of searching through the list itself, okay, the indices, okay, so our output is indices. Our output will be mainly indices. So the possible output will be 0. So the possible output will be some subsets of 0 all the way to some 0, 1, 2, all the way to length of L minus 1. These are all the indices. Okay, so what we are searching for is basically indices that we are searching for. So essentially, we are searching through the indices of L. So when we iterate through the indices of L. At each iteration, check if the element at the index is equal to X. If yes, print out the index, and then we continue with the next index. Okay. So again, it's a very minor modification. Okay, because the output will be one of these values. So this is our search space now. It's not the list L itself, but rather the indices of L. Okay. So again, it's very simple. So for I in range, so this is by now it should be a second nature to you to write for I in range certain thing. The indices will be starting from 0 and length of L. Remember, this will generate integers from 0 to length of L minus 1 inclusive. And these are all the indices of L. Okay, so for each one of them, you're gonna check if the value at Li is equals to X. If it is, you found it, you're gonna print the index. Okay, but you don't stop because you want to keep on looking for the next index of occurrence. You want to look for all indices all positions of L that contains X. Okay, so at the end of the iteration, you don't do anything. So these are all the indices for which X occur in L. It say that X occur in index 0. Index 0 has value 1, which is the target value. Index 4 should have value 1 also. So this is index 0, 1, 2, 3, 4. Okay, and this is index 5, index 5, index 6 also contains the value 1. Okay, so again, all of these similarly not searching, but you are basically using the same blueprint of searching. Okay, now the final example, which is the one that is very interesting, is to check for duplicates. Okay, now what is duplicates? So basically you are given a list L and you output true if L has duplicates, that is values that occur more than once. Okay, so for example, if you are given this list here, okay, it has duplicates because there are values that occur more than once. For example, 1 occurs 7 times, and we have seen before, and 2 occurs 2 times. Okay, so it has duplicates here. And this list here contains only unique values, 1, 2, 3, 4, 5. None of them occur more than once, so it has no duplicates. Okay, so here, if it has duplicates, we're going to output true. Otherwise, we output false. Okay, so again, if you look at these questions, when you want to check whether it has duplicates, we somehow also do searching. Okay, so we also perform searching. Okay, so the question is, what are we searching for? What is the search space? Okay, and what happened, and what is the property once you found it? Okay, once you found it, what is the output? So these are the questions that we want to ask when we want to perform this task here. We know we're going to perform a search, but what are we searching for? We are searching for a duplicate. But what's this duplicate going to be? How do we know? How do we know which elements occur more than once? How do we do it? How do we write an algorithm or instruction for the computer to help us to check whether it has duplicate values? Okay. Now the idea is that we're going to come up with different versions, and each of these versions is somehow using different search space. Okay, and based on this, we're gonna do an informal analysis of which version is better. Okay, so the idea is, first, suppose that we know that the list is a sequence of 500 integers and random integers from 0 to 9,999. Okay, so I have a list that is generated randomly. Okay, so X, I'm going to use import random. So the following code, you don't have to know. Okay, this is beyond the scope. I'm just going to write it down here. Okay. All right, this is basically, right, you don't have to know what it does. Sorry, you don't have to know every single thing in this syntax here. Basically, what I did is create a new list where I generated 500 random integers, and each of these integers is from this range here. It's with 0 to 9,999 inclusive. Okay, so when I do range, okay, it's from 0 to 10,000. That is because because it will exclude 10,000, but it will include 9,999. Okay, so let's print L. Okay, so this is my random list of 500 elements. All right, print length of L. All right, you have 500 random elements. Each of them is in this range here, 0 to 9,999 inclusive. Okay, and then I want to check whether it has duplicates. Okay, now there are 500 elements here. Now, if you just look eyeballing it, it's very hard to tell whether it has duplicates. So we need to write an algorithm to solve these problems. We don't do it manually. We don't look at it and check whether it has duplicates by ourselves. Okay, so again, what is the idea? The version 1 here is that I want to look for Okay, so if a duplicate exists, what is the possibilities of the duplicate? There is the non-unique value. Okay, so what is the non-unique value that could exist? Okay, so since every element in L is come from this range here, which is 0 to 9,999 inclusive. So it can only be one of these values. Okay, since, so answer, since all elements in L is between 0 to 999 inclusive. Okay, the non-unique elements, a duplicate value or non-unique value has to be one of these elements. Right. So you know that the search space I'm looking for in this case, if I interpret it this way, okay, if I interpret it this way, since the duplicate, we want to output one duplicate value, whether it exists or not. But we don't know what is this duplicate value, but we know the possibilities. It has to be from 0 to 9,099 because every element in L is from this range here. So my search space would have to be range of 0, 10,000. This is range 0, 10,000 in Python is the same as 0 to 9,999 inclusive. Okay, so for each of these elements here, I'm going to check whether it occurs more than once in the list. Okay, so for each of these possibility, so we are going to examine if the value is occurs more than once in the list. Okay, if it is, then it is the duplicate. If it is, then we found a duplicated value. We found duplicate value. Okay, if not, we're gonna continue with the next possibility. All right, so the property of duplicate is that it occurs more than once in the list. Okay, when we found duplicates, okay, we can just output true and exit because we don't have to keep on continue looking for it. Oh, so actually output the value and exit. Once we found it, we just output the value that it's a duplicate, it occurs more than once, and then we exit. When no duplicates are found, after checking all the possibilities, we just, for example, output false, or output a message, or display meaningful message. Display message indicate no duplicate. Okay, so this whole idea of if you interpret finding a duplicate in this way, and you interpret that the output must be one of the value in the list, and since every element in the list is in this range, so your possibilities must be in this range, then your search space is in this. Okay, and then for every single element in this range here, you're gonna check whether it occurs more than once in the list. If it is, you found it, you output the value and then you exit. At the end of the iterations, you exhaust all the possibilities. Okay, then you say there is no duplicate here. Okay, so let's write it down. Okay, so let's implement this. All right, so we're gonna have run through a search space. So everything is basically the same as searching. All right, except we're gonna change the search space, and then we're gonna change what we do when we found it, and so on. Okay, so for I, also for value in the range, our search space is range of 0 and 10,000. This is our search space. Okay, and then what we are looking for if it occurs more than once in the list. So if it's not just value in L, this will only check whether it's in L, but we don't know how many times. So if we want to know how many times it's occurred, we do dot count. if L.count value is more than 1, okay? If it's more than 1, this value is the duplicate value, okay? Then you print the value. This is the non-unique value, and then you break. At the end of the iterations, okay, you just print a meaningful message. All elements are unique. All elements in L are unique, or they occur only once time, one, okay? So let's hear. It says that 186 occur more than once in the list, okay? Okay. Let's see. I make a mistake here. Okay. Has duplicate. So again, I forgot to initialize the value here. Has duplicate initialized to false, okay? And duplicate should be equals to true now once we found it. And if not has duplicate, if it doesn't have duplicate, then you print out that it's none of the value has none of the value is occur more than once. That is the same as saying all elements in L are unique. Okay, so again, it's very important. We have a Boolean variable before that to indicate first is initialized to false. Once we find it, we flip it to true. Okay, so here it indicates that 186 is actually a duplicate value. But if you look at the list here, it's very difficult to find, to realize that 186 is actually occur more than once. Early on, I just see 186 occur once somewhere. And then if I want to go through it again, I'm going to have to go through it. So this is occurring one time. And if I keep on scrolling it, maybe I will find 186 again. Okay, but as you can see, with 500, here is another 186 somewhere here. Okay, as you can see, it's not that easy if you do it manually. That's why we learn how to write program to solve these problems. Okay, and if you see here, this code have the similar flavor as before. That is, you want to search something, but you need to identify what is your search space, what is the property you are searching for, and once you found it, what do you do with it? Okay, so these are the ideas. Now we can extend this idea further. If I want to know which values occur more, so this is done. Okay, we can expand it further. How many non-unique values? That means how many such values that occur more than once. Here we only identify one value, 186 occur more than once. Could there be any other value that occur more than once in this list? Okay, so again, it's like first we do searching and then we modify it to do counting. So the idea is the same. We found one element, which is a duplicate value, and then we want to extend it. We want to count how many duplicate value exists in the list, how many non-unique value in the list. So again, you know that it's a simple modifications of this code here. Okay, so again, we'll use the same blueprint. Okay, just making modification. Again, we are looking for, these are all the values, possible values of duplicate exist, because every element in L is from this range. And property of duplicates, again, is the same. If it occur more than once in the list, then it's a duplicate, it's a non-unique value. And what happened when I found it? Now, because I want to count how many of non-unique values, so I don't just output the value and exist. Just like counting, I'm going to add 1 to count. Okay, so I'm going to say create a variable, the same as counting. So if you remember, we have count here, we have a blueprint for counting. Okay, where we have here, okay, we create a variable called total, initialized to 0. When we found it, we add 1 to total and then continue. So that's the same idea. We just borrow that idea to our counting number of elements here. Okay, so when we found the duplicates, so first we create a variable, say count or total. Okay, initialize to 0. So at the beginning is 0. Okay, and when we found the duplicates, we add 1 to count. Okay, and then we continue. We don't stop because we want to keep on checking whether there is another duplicate. And then if there is, we're going to add 1 to count. Okay. So very simple modifications of the previous code. So again, here has duplicate equals here. We're going to borrow exactly the code, but we're going to change this part. Say count is equals to 0. Okay. If once you found it, you do count plus equals to 1. Okay. And then you don't break because you want to continue to check whether there exists another element here. Okay. So if count is equals to 0, that means no value, you didn't find any non-unique elements. There is no duplicate. That means count will remain at 0. Then you will say that all elements in L are unique. So let's print count 2 as well. Else you print count. Okay, there are 11 such duplicate values. So besides 186, there are 10 other values in L that occur more than once. Okay, so in total, there are 11 elements in L that occur more than once in the list. All right, so this is version 1. All right, where our search page is actually from range 0 to 10,000. So again, when we look at an algorithm, we always analyze how much time it takes to run this algorithm. Is it efficient enough? Can we optimize it? So one thing that we can do when we analyze the code is to check how many times or how many iterations. Okay, so how many iterations of executed, how many iterations are there? Okay, how many times we run this repeated code? How many times we run it? So because this is from range 0 to 10,000, so you know that you run 10,000 times. Okay, so the number of iterations is 10,000. Okay, so you can assume that we're gonna have 10,000 steps. Okay, but this is not indicative enough because in each iteration, you also have some other methods here. Okay, so at each iteration, you run L.count, which also consume some computational steps. So behind the scene, L.count is doing something. Okay, so it depends on how L.count is implemented. But if you look at our own count algorithms, okay, if we look our own count algorithms here, we basically look through every element in L again. Okay, so question is, how many? So what we wanted to know is that the atomic unit computation step, how many times it takes. Okay, so how many times element in the list is examined in the worst case. So this is to do. So go home and think about it. We're gonna come back to this again. So we'll continue from here. Okay. Thank you, class.